Hey everybody, welcome to another Calc Ready video. And today we're actually going to take a little break from calculus and we're going to do a little proof. And the reason we're going to do that is because I just took a discrete math test today and this question made me really happy. So we're going to be doing this together on the board. Yeah, and it's on mathematical induction. Mathematical induction. So this is a method to prove things across the natural numbers, and it has 3 steps. So I'm just going to call them I1, I2, and I3. So I1 is our base step. Basically, when you're using mathematical induction, you're proving something on the set of natural numbers. So 0, 1, 2, 3, 4, 5, 6, and so on and so forth. Base step, you're always going to assume that n is equal to 1, and that's going to be the base for your proof. So if something is true for the first natural number, and then you can prove that it's true for n plus 1, so the second natural number, that means it's going to be true across the whole range of natural numbers. I2 is our second step. That's going to be our induction hypothesis. You're going to assume that the question that you're given is true, and then prove it for n plus 1. And you actually do that in the third step, which is the induction step. So it's going to be more clear once we get into the actual example, so I think we should start doing that. Yeah. So I think the question was something like this. It was proved that k is equal to 1, k plus 1 to n is equal to n times n plus 1 times n plus 2 over 3. I think it was something like this. For all n is an element in the natural numbers. Yeah, so how are we going to start proving this? Well, we're going to take our first step, right? Our base step, I1. And we're proving this for our first case. Our first case is whenever n is equal to 1. So we basically have to prove that this equation right here is true whenever n is equal to 1. And how do we do that? We just plug it in, right? So we have our sigma from k is equal to 1 to 1 of k plus 1. Here we just plug in 1, so we have 1 times 1 plus 1. Oh, sorry, this is a 1. 1 plus 1 is equal to 1 times 2, which is just equal to 2. And then we also have to plug it in for here, right? So we're going to have 1 times 1 plus 1 times 1 plus 2 divided by 3. This is 1 times 2 times 3. So this is just equal to 2. So left side, right side is equal. That means our base case holds. We can just put a little check mark and move on to step number 2. Oh, my board isn't really big, so we're going to be erasing the step because step number 3 does take a little bit more space. But okay, step 2 is the shortest. That's your induction hypothesis. Here you're just going to assume that this right here is true for some n is equal to m. So we're going to assume this, and we're going to change the variables so it's less confusing. We're going to change the n to m is equal to m times m plus 1, m plus 2 over 3. For some m is equal to n. Just for some natural number. And that's it. That's our second step. So we're done with that. Now we're gonna get into the actual proof in step number 3. So yeah, we've proved that this is true whenever n is equal to 1. Now we're gonna prove that it's true for when we're going up, when it's true for the first natural number, second, third. And how we do that is we just add 1. So again, we assume that it's true for some m. Now we have to prove that it's true for m plus 1. If it's true for m plus 1, then it's true for any other natural number. So we're just going to do this. K equals 1, and then not m this time, but m plus 1. And then keep everything inside as it is. K plus 1. And again, remember we put m plus 1 for m, so that's what we're going to do here. We're going to have m plus 1. We're subbing m plus 1 for this m. And we're going to do the same thing for this m. So this bracket is going to turn into m plus 1 plus 1, so m plus 2. And this is going to turn into m plus 1 plus 2, so this is going to be m plus 3. And once again, over 3. So now, basically, the point of this proof is to show that this is the exact same thing as this for all m plus 1. We can split up the sigma notation, and we can split it up like this. Remember, this just means repeated addition. So we're gonna add everything up to m. We added everything up to m, and now we have to add up everything from m to m plus 1. So that means we can just add and sub this in. So we have m plus 1, we're subbing that in for k, m plus 1. And if we sub in m plus 1 to here, we're going to get m plus 2. This is like, if you haven't worked with sigma notation for a long time, for some time, right? This is the hardest step because requires knowing properties of sigma notation. So if this confuses you, just go over your sigma notation. But think about it this way. Here we're subbing everything, we're adding everything from 1 to m, and here we're adding everything from m to m plus 1 in this part right here. And now I'm going to stop writing this because our goal is to show that this is equal to this. And we have to make this look exactly like this. So I'm going to stop writing equals to this just to save us some space. So what can we do? Well, we know by induction hypothesis that this is equal to this. That was our hypothesis. So we're going to do that. We're going to sub in this for this. So we're going to write m plus 2 over 3 plus this statement right here. M plus 2. And now we're going to add, we're going to find the common denominator, which is 3. So, see, I don't have a lot of space. Let me go back on the top. So we're going to multiply this here by 3. So m times m plus 1, m plus 2 over 3 plus 3 times m plus 1, m plus 2 over 3. Our denominators are the same, so we can add. So we just add everything else on top. M plus 1, m plus 2, plus 3, m plus 1, and m all over 3. So yeah, now we're right here, and I'm gonna write the final step in this box. Yeah, now we're gonna have to do some algebra again. So since we have m plus 1 in both of these parts in the addition, we can factor that out. Same thing with m plus 2. They're in both sides, and we're going to be factoring out. So we're factoring out m plus 1, factoring out m plus 2. If we take this out, this out, this out, this out, everything that's left is just m plus 3. And our denominator of 3. So congratulations. Oh, this is going to be 3. So we've made this whole thing look exactly like this thing. And it's a little confusing to understand because, like, you might be asking, oh, isn't this just going in a circle? We assume this is true, so how can we use that to assume that m plus 1 is true? And honestly, I don't really know. Like, I'm gonna have to consult my math book. But yeah, this is how you prove something by mathematical induction. There's also examples with factorials, which are probably even better. But I really like this one because it was on my test, and when I saw it, I was very happy that I got this question because like it clicked in my head right away. But yeah, I hope you guys join me in another math video soon, and yeah, I hope I see you later.